Okay, let's talk about something I bet almost everyone listening has run into. You've poured hours into writing some, amazing Python code. You finally get it running perfectly on your machine, feeling pretty good about it, and then you share it, maybe with a friend, or you try to deploy it to a server, and you get hit with those words you just dread. Uh-oh, it doesn't work on my machine. Or maybe you've just found yourself staring at your terminal, totally lost, trying to figure out which tool you're even supposed to be using. Is it pip? Is it venv, vescv, conda, poetry? I mean, the list just seems to go on and on. If that sounds familiar, seriously, you are not alone. This is that often confusing, sometimes really frustrating world of Python's package management. People even call it, well, dependency hell. Hmm. All right, so our mission today is to cut through all that noise. We're going to dive deep into this whole ecosystem, try to demystify it a bit. We want you to understand why it got so complicated or diverse, what the main tools actually are, and probably most importantly, figure out which tool you should be reaching for depending on what you're trying to build. We've pulled together insights from a really comprehensive audio guide on this whole topic, looking at how things evolved historically right up to the very latest stuff, all tailored for you. So let's really start with that feeling, that almost universal experience. The pip install gamble. You type it, you cross your fingers, and you just kind of hope for the best, right? But then maybe a project that worked perfectly fine yesterday just suddenly breaks today. Or you can't get that new library you want to use to cooperate with an older one you already have installed. It's incredibly frustrating, isn't it? And for anyone trying to build, serious Python applications, it really feels like a fundamental roadblock sometimes.
Well, absolutely. It really is. And that moment, that really common experience where your code just behaves differently depending on where it's run, or even on the same machine, just at a different time, that points directly to this core set of problems. Problems that package managers are specifically designed to solve. It's not just like a minor annoyance. It's actually a critical challenge if you want your work to be reproducible, easily shareable, reliable.
And that whole mess that it works on my machine, nightmare, it actually has a name, right? You mentioned it. Dependency hell. To make this feel a bit more real, let's try a simple analogy. Imagine you're building something really complex with Legos, maybe a huge spaceship or, I don't know, a giant castle. Now, each of those projects needs specific sets of bricks and crucially specific versions of those bricks. Like you need the 2x4 blue bricks from the 2020 set, not the 2019 ones. So, what happens if you just dump all your Legos from every set you've ever owned into one massive box? Just mix everything together. Well, when you go to build something new, you might grab a brick that looks right, but it actually conflicts with one you already used in your finished spaceship. Suddenly, maybe your spaceship's wing falls off or your castle tower crumbles because you unknowingly swapped an old, essential piece for a newer, slightly different, incompatible one. And that's pretty much exactly what happens with Python dependencies. You might have project A and it absolutely needs, say, pandas version 1.5, but then you start project B and it needs the latest and greatest pandas version 2.0 or maybe even newer. If you try installing both of those globally, right onto your main system Python, well, you hit what's called an irreconcilable conflict. Only one version can live there at a time. And before we had better solutions, installing packages globally like this made your system's Python incredibly fragile. You install one thing, and suddenly scripts that worked fine yesterday are broken. Plus, for real reproducibility, which is kind of the holy grail in software development, making sure your code runs exactly the same way everywhere on your machine, your teammate's machine, the server simple requirements.txt files often just don't cut it.
Yeah, that's a really key point. They often fall short because they don't explicitly pin all the transitive dependencies.
Right, the dependencies of your dependencies.
Exactly. The packages that your packages rely on. And they often don't include those cryptographic hashes for verification either. So if one of those subdependencies gets updated, even a tiny patch version, your requirements.txt might not even notice. And boom, you're right back in that it works on my machine scenario. And what's really fascinating, I think, is looking back, these problems aren't actually new. They've been evolving for decades. And the tools we use have been evolving right alongside them, trying to catch up. Think way back, like late 1990s, Python's pre-CPAN era, if you will. Distributing code was just, well, pure chaos. Developers would literally upload their code files manually to websites, maybe FTP servers. They'd provide these often really complicated manual installation instructions. There was no central place to find packages, no automated way to install them. It was a huge barrier to actually reusing code, especially when you compare it to what Perl had with CPAN, which was already quite sophisticated. So that early chaos really highlighted this desperate need for some kind of standardization. The first big step came around the year 2000 with distutils. That got built into Python 1.6. It introduced the setup.py file for packaging code, which was foundational, a huge step, but it still didn't have a central index, a place to actually find all these packages. Then came setuptools and easy install. They were definitely improvements. They offered automated installation, which was great. But it kind of led to their own problems, this sort of dependency chaos, because everything was still being installed globally into the main system Python. This just cluttered everything up really quickly, made systems fragile, and often meant you needed root or admin privileges just to install or update a library, which is, not ideal. So all this constant breaking of environments, it led to this really critical question. How do we keep projects separate? How do we isolate them? And the breakthrough answer came in 2007 with virtualenv, created by Ian Bicking. This tool introduced what was, at the time, a really revolutionary concept: isolated Python environments. Suddenly, each project could have its own little self-contained world, its own directory with its own specific Python interpreter, and its own site packages folder for libraries. This was an absolute game changer. Project A's dependencies couldn't possibly clash with Project B's anymore. They lived in totally separate universes. And this idea, this concept of isolated, almost disposable environments, it became, and honestly it still is, a cornerstone of modern Python development. It just eliminated so many of those recurring headaches for developers. And building right on that momentum, in 2008, Ian Bicking also developed PyInstall, which very quickly got renamed to pip. Now, pip was designed from the ground up to be a much better, more reliable replacement for easy install. And it introduced that now totally ubiquitous requirements.txt file for listing out a project's dependencies. The combination of pip and virtualenv, it just took off. It rapidly became the de facto standard way to manage packages and environments in Python. It was so widely adopted, in fact, that the PyPA, as the Python packaging authority, they officially took over, maintaining both pip and virtualenv back in 2011. That really cemented their roles as the core tools for many years. But, even this powerful duo, pip plus virtualenv, it wasn't perfect. It still had limitations. Managing those virtual environments still felt a little bit manual, creating them, activating them, remembering which one you were in. And the requirements.txt file, especially the ones generated by just running pip freeze, they weren't always truly deterministic, especially for more complex projects with lots of nested dependencies. You still end up with slightly different environments. And this friction, it really spurred the next major wave of innovation in Python packaging. We started seeing these integrated sort of all-in-one tools emerge, things like pipe and viv, and perhaps most influentially, poetry. These newer tools really championed using the pyproject.toml file. This is now standardized by a formal Python enhancement proposal, or PEP, specifically PP 621. So the shift towards using pyproject.toml as a central configuration file, along with using robust lock files for really deterministic builds. It wasn't just about fancy new tools. It signaled a really crucial move away from fragmented, kind of ad hoc configurations towards a more unified, consistent, and predictable Python ecosystem for everyone involved.
Okay, so if that really paints a clear picture, we can see exactly why virtual environments are just that absolute first line of defense. They're non-negotiable, really. They stop that system contamination. They prevent those version conflicts by giving every single project its own little Python sandbox to play in. And like you said, since Python 3.3, we've had venv built right into Python itself. So that's now the officially recommended way to create these isolated spaces. You just run a simple command like python-mvenv.venv right in your project directory. And bam, it creates this self-contained environment for you. Then you activate it with another command. It's slightly different on Windows versus Mac or Linux, but it's simple. And that ensures that when you type Python or pip, you're targeting that specific environment, not your global system Python. And when you're done working on the project, you just type deactivate. Easy. Now, virtual, the original tool, it was the Pioneer, and it's definitely still maintained and has some extra features. But for many cases, the built-in ven is perfectly fine and doesn't need you to install anything extra. But here's the really crucial point, I think. Virtual environments are absolutely critical for isolation, but they alone don't automatically solve that problem of guaranteeing perfect reproducibility across different machines or different times. And that's where this next generation of tools really comes into play.
Right. So now that we've got a solid grasp on why this whole dependency thing is a challenge, and we understand the foundational solution of virtual environments, let's pivot. Let's look at the modern landscape. What are the main tools that have emerged? Building on top of that foundation, think of them maybe as like specialized power tools. Each one has a different philosophy, maybe a different way of working, and they're designed for slightly different jobs.
Exactly. That's a great way to put it. So let's do a quick tour. We'll give you a concise overview of the main players, highlighting their core strengths, where they shine, and maybe where they have some limitations, just so you can see their distinct roles in the ecosystem. Okay, first up, the one pretty much everyone encounters, pip, the ubiquitous installer. This is Python's standard package installer, right? So it comes bundled with Python itself since version 3.4. Its main job, its core function, is to install packages directly from PyPI, the Python package index. Its biggest strength is just that it's ubiquity. Everyone using Python has it, and it's simple to use. Generally.pip install whatever package is straightforward, and it connects seamlessly to PyPI. But there are limitations. It's primarily designed for pure Python packages. It doesn't really handle non-Python dependencies like C libraries that need compiling very well, or at all sometimes. And while its dependency resolver got a major upgrade back in 2020, which was a huge improvement, those classic requirements.txt files, well, they're often just what we call flawed snapshots. They don't truly lock down all the versions, especially those hidden transitive dependencies. And they don't typically include cryptographic hashes by default for verification. This can absolutely lead back to those reproducibility issues. And crucially, remember, pip itself isn't an environment manager. It relies on you using venv or virtualenv separately. For better requirements.txt files, ones that do act like proper log files, people often use an extra tool called pip tools alongside pip. Okay, next up, conda. This is often called the scientific and cross-language powerhouse. Conda is open source. It works across platforms, Windows, Mac, Linux. And here's the really critical differentiator. It's language agnostic. What's really powerful about Conda is that it treats Python itself as just another package it can manage. And it mostly relies on pre-compiled binary packages. This means it often bypasses the need for you to have complex compilers set up on your local machine, which is a massive, massive advantage, especially in the world of scientific computing. Its biggest strength is definitely handling those complex non-Python dependencies. Things written in C, C++, down Fortran, or even proprietary libraries like Intel's MKL for super optimized math, or NVIDIA's DUDA for GPU computing. These are essential for core data science libraries like NumPy, SciPy, TensorFlow, PyTorch. Conda also has integrated environment management built right in. You use conda commands to create environments, activate them, install packages. It's all handled by one tool. It also makes managing different versions of Python itself really easy, and it uses these things called channels, like the popular Conda Forge, which are like alternative repositories for community-maintained packages. Now, what are the downsides to Conda? Well, it generally has a larger disk footprint than picvenv setups. And this brings up a really important point we need to stress. Mixing pip and conda inside the same environment can get really tricky. The reason is that conda's dependency resolver isn't really aware of packages that you install using pip. This can lead to some really frustrating, hard to diagnose conflicts down the line. So the best practice, the strong recommendation is always install everything you possibly can using conda first. Only then, if a package is absolutely missing from conda channels, should you resort to using pip inside that conda environment. Oh, and one more clarification. There's Anaconda, which is this huge distribution that comes with hundreds of pre-installed packages, often used by beginners. And then there's Miniconda, which is just the minimal conda installer plus Python. Generally, for cleaner, more tailored environments, starting with Miniconda is the recommended approach. Okay, moving on to the more modern all-in-one tools. Let's talk about Poetry, often described as the modern application developer's toolkit. Poetry is known for being quite opinionated. It's designed to manage your entire project lifecycle, from creating a new project structure all the way to publishing your library to PyPI. And it tries to enforce best practices along the way. Its absolute core strength is its deterministic dependency resolution. It generates a file called poetry.lock. This file records the exact version down to the specific commit hash sometimes, and includes cryptographic hashes for all dependencies, direct and transitive. This guarantees perfect byte-for-byte reproducibility across different machines and different times.
It uses that pyproject.toml file as a single source of truth for all your project metadata and dependencies, replacing the need for older files like setup.py, requirements.txt, manifest.n, etc. Poetry offers this really nice, fully integrated workflow with commands like Poetry need to start a project, Poetry add to add dependencies, Poetry run to execute scripts in the managed environment, Poetry build, and Poetry publish. It also has built-in support for cleanly separating your main dependencies from your development-only dependencies. What are the potential limitations? Well, because it's opinionated, there can be a slightly steeper learning curve compared to just using pip. And it's primarily Python-centric, meaning it doesn't really help you manage system-level dependencies like conda does. All right, next in the modern category is Hatch. You could call this the Extensible and Standards-Aligned Project Manager. It's similar in scope to Poetry, aiming to manage the whole project lifecycle, but it has a slightly different philosophy. Hatch really emphasizes extreme extensibility and very strict alignment with the official PyPI standards.
Its key differentiator, its main strength, is probably its extensibility via plugins. Hatch allows you to write custom hooks that can plug into various parts of the build process. This is really powerful if you have complex build requirements, maybe involving non-Python code compilation or generating files dynamically. If you need fine-grained control, Hatch provides it. It's also meticulously standards compliant, especially regarding PPP 621 for the pyproject.toml file. Hatch also offers really powerful environment management features, including support for multiple named environments for different purposes, like testing against different Python versions, and it integrates very efficiently with newer tools like UA. Now, the limitations: it's a bit newer than Poetry, so the community around it is smaller, though growing fast. And here's a crucial difference. Hatch does not have its own native log file mechanism. To get that guaranteed reproducibility, you need to combine Hatch with other tools, typically pip tools or the aforementioned live. Also, because it's less opinionated than Poetry, it might feel a bit harder for beginners who sometimes prefer more built-in guardrails. Then there's PDM, which stands for Python Development Master. This is another strong contender in that modern all-in-one manager space. It often draws inspiration from the JavaScript world, specifically NPM. What's really compelling about PDM is its unwavering commitment to adhering strictly to the latest official Python packaging standards, the PEPs. A key aspect is that it works seamlessly with any build system that follows the modern standard, PEP 517 build backends. This gives it a bit more flexibility in some complex project setups compared to, say, Poetry. PDM even offers experimental support for a concept called PEP 582, which aims for a venv-less development workflow, although its default behavior is still to use standard virtual environments. It also offers flexible ways to specify dependency versions and, importantly, generates a robust pdm.lock file for that crucial reproducibility. What about drawbacks? Similar to Hatch, its primary limitation is probably just having a smaller market share and community compared to Poetry, which might mean fewer readily available tutorials or quicker answers to niche questions online. But it's a very solid standards-focused tool. Okay, and finally, we arrive at the newest and arguably most disruptive tool on the block, UV, the Rust-powered speed revolution. This is a really exciting one. It's developed by the same team that created Rough, the incredibly fast Python linter that has taken the community by storm. UV is designed as an extremely fast package installer and dependency resolver, and the key is that it's written entirely in Rust. Its defining feature, hands down, is performance. We're talking seriously fast. Benchmarks often show it being 10 to even 100 times faster than using the traditional pip and venv combination for common tasks like creating environments and installing packages. This speed comes from Rust's inherent performance, but also clever parallel execution during downloads and installs, and a highly optimized dependency resolution algorithm. UV aims to be a unified toolchain packaged in a single small binary. The goal is to eventually replace pip, pip tools, and venv entirely. Just one tool to rule them all, essentially. It also features intelligent global caching of downloaded packages, which saves a lot of disk space if you have many projects, and dramatically speeds up subsequent environment creation or package installation if the package is already cached. Is it perfect yet? Well, it's still evolving rapidly, so features and APIs are expanding. And like pip, Poetry, Hatch, and PDM, is primarily Python-centric. It doesn't handle non-Python system dependencies. But its game-changing speed makes it incredibly compelling, especially for tasks like speeding up slow CI/CD pipelines or just making your local development workflow feel much snappier. It can significantly cut down on cloud infrastructure costs, too.
Wow, okay, that's quite a tour. It really is fascinating, isn't it? How each of these tools kind of carved out its own niche, evolving to solve very specific pain points that people were feeling. And like you said, it highlights that there really isn't one single best tool for everyone. It's more like having a toolbox with a spectrum of options for different kinds of jobs.
Exactly. Which brings us to the crucial question, right? For everyone listening, how do you actually begin to choose the right tool from this, well, slightly overwhelming array of options? This seems to be where understanding your project's specific needs, your context, becomes really, really key.
Absolutely. Let's try to break it down into some common scenarios. Hopefully this will give you some clear, actionable advice based on what you're actually trying to do. Okay, scenario one.
I'm just writing a simple script, maybe exploring a new library, nothing too complex. Recommendation. For this, honestly, just stick with pip plus venv. Reasoning. It's built right into Python. There are no extra tools you need to install or learn. It's absolutely the path of least resistance for straightforward tasks or just quick experimentation. It gets you up and running fast without cluttering up your main system Python. Simple, effective. All right, scenario 2. I'm a data scientist. My daily bread involves NumPy, Pandas, maybe scikit-learn, and definitely heavy hitters like TensorFlow or PyTorch. Recommendation. In this case, you should almost certainly be using conda and specifically start your projects with mini conda. Reasoning. Your work fundamentally relies on those complex compiled non-Python dependencies. We talked about things written in C, Fortran, needing CUD support for GPUs, or Intel's MKL for optimized math. Pip just isn't designed to handle these effectively or reliably. Conda provides pre-compiled binary packages that usually just work out of the box, saving you potentially hours of painful compilation errors. And starting with mini conda keeps your environments clean and tailored, avoiding unnecessary bloat. Okay, scenario 3. I'm building a modern web application using something like Django or Flask. Or maybe I'm creating a Python library that I intend to publish on PyPI for others to use. Recommendation. Here you'll likely want to reach for poetry or PDM. Reasoning. For these kinds of projects, things like strict reproducibility, having a clear separation between your development tools and your production dependencies, and having a streamlined process for building and releasing your package are absolutely essential. Both poetry and PDM excel in these areas. They both leverage pyproject.toml for configuration and generate robust log files, poetry.lock or pdm.lock, to guarantee identical environments everywhere. Poetry is currently more widely adopted and perhaps a bit more opinionated, which some prefer. PDM offers stricter adherence to the latest Python standards and maybe a bit more flexibility in its choice of build backends. Both are excellent choices here. How about scenario 4? I'm a library author, but my library has a really complex build process. Maybe it involves compiling C++ extensions, or generating code automatically during the build, or I just want maximum control over every step. Recommendation. For this situation, you should seriously consider using Hatch. Reasoning. Hatch was fundamentally built with flexibility and extensibility in mind. If your project requires custom build steps, maybe you need to compile non-Python assets, run code generation scripts, or integrate tightly with other language toolchains. Hatch's powerful plugin system and its built hooks give you that fine-grained control that more opinionated tools might abstract away or make difficult. Plus, its deep alignment with PyPI standards makes it a very robust choice for complex standards-compliant library builds. And finally, scenario 5. My CI/CD pipeline is painfully slow. Installing dependencies seems to take forever, eating up build minutes and delaying feedback. Recommendation. Definitely look into integrating of reasoning. As we discussed, Yive is an absolute performance game changer.
It's designed as a largely drop-in replacement for pip and venv, but it's often dramatically faster, 10x, 50x, sometimes even 100x faster. Integrating it into your CI/CD workflow can drastically cut down build and test times. This translates directly into faster feedback loops for your developers, enables more frequent deployments, and can even lead to noticeable savings on your cloud infrastructure bills. That efficient global caching it does is also a huge win for repetitive CI builds.
That really does make the choices much, much clearer. It feels like it puts the power back in your hands, letting you pick the right tool for the job you're actually doing. And it's probably worth quickly re-emphasizing that point you made earlier about tool interoperability, especially that specific caution about using pip inside a conda environment. Just to remind everyone, conda's dependency resolver doesn't know about things installed by pip, and mixing them can lead to some really subtle, hard-to-debug conflicts later on. So the advice stands. Always try to install as much as you possibly can using conda first. Only use pip as a last resort if a package simply isn't available through any conda channels.
Yeah, absolutely critical advice. And if we sort of zoom out and connect this all back to the bigger picture, the complexity we've been discussing here, it isn't really a sign of failure in Python's ecosystem. I think it's actually a direct reflection of Python's incredible power and its versatility. The reason there isn't one single best tool that fits every single use case is precisely because Python is used for such an astonishingly vast and diverse range of problems, from simple scripts to complex web apps to cutting-edge AI research. The right choice is always contextual. It depends entirely on your specific project's needs, constraints, and priorities.
That makes perfect sense. So regardless of which specific tool, pip, conda, poetry, hatch, PDM, UV you end up choosing for a particular project, there are some universal best practices that kind of cut across all of them. These should probably be your guiding stars. First, and we've said it before, but it bears repeating because it's truly non-negotiable, always use virtual environments. Always. They are the absolute fundamental rule for isolating your projects, protecting your system Python, and avoiding those dreaded dependency conflicts. Use venv or virtualenv. Second, pin your dependencies with a lock file. If you need true bulletproof reproducibility across different machines, different operating systems, different points in time, this is essential. Whether that lock file is called poetry.lock, pdm.lock, uv.lock, or even a meticulously generated requirements.txt from pipcompile, you need something that locks down the exact versions of everything. Third, try to understand your PyProject.tom model. This file is rapidly becoming the new center of the Python packaging universe, thanks to PEP 621. It's becoming the unified place for defining project metadata and configuring various tools. Getting familiar with it is increasingly important. Fourth, make sure you separate production and development dependencies. Keep your deployments lean, fast, and secure by ensuring that things like testing frameworks, linters, or code formatters don't get accidentally shipped to your live applications. Most modern tools make this easy. And finally, fifth, establish a process to regularly update dependencies. While pinning versions gives you stability, you also need a strategy to periodically update your dependencies to pull in crucial security fixes and benefit from new features and performance improvements. And, of course, always test thoroughly after updating before pushing those changes.
Absolutely. Those are the core pillars, really. And what's really exciting, I think, is that the Python packaging landscape isn't static. It's in a period of really dynamic and rapid evolution right now. And it seems to be driven by two clear and powerful trends. The first is this strong convergence on standards. The widespread adoption of PyProject.toml for project metadata and configuration, largely driven by PP 621, means that Python projects are becoming more consistent and more interoperable, regardless of which specific management tool you happen to be using. This really simplifies things in the long run for everyone in the ecosystem. And the second major trend is performance becoming a core feature. The incredible rise of these Rust-powered tools like R for packaging and Rough for linting, which just dramatically speed up common development workflows, this is pushing the entire ecosystem to become more efficient. This intense focus on raw speed isn't just some niche optimization anymore. It's fundamentally changing developer expectations. People are realizing they don't have to wait minutes for dependencies to install. And it's delivering really tangible benefits, especially in areas that used to be bottlenecks, like continuous integration and deployment pipelines.
Yeah, it feels like a really exciting time, actually. So ultimately, taking the time to understand these tools, their strengths, their weaknesses, it really allows you, the developer, to make informed decisions. It helps you build Python applications that are robust, reliable, and that genuinely work on everyone's machine, not just yours. It transforms what can initially feel like this confusing, maybe even intimidating landscape into a powerful, much clearer toolkit that you can leverage effectively. So, thinking about that rapid evolution you just mentioned, here's a final thought to leave our listeners with. Given how fast Python packaging is evolving, what do you think might be the next really big challenge that the community needs to tackle in this space? And how might solving that challenge shape the tools we'll be using in, say, the next 5 years?
Ooh, that's a great forward-looking question. And it's definitely something developers and tool authors are actively thinking about. If I had to guess, I think the next major frontier, the next big challenge will likely be further refining the experience around managing platform-specific dependencies and compiled extensions in a more universally integrated way. While Conda does a fantastic job of this, especially for the scientific Python stack, achieving that same level of seamlessness for all types of Python projects, web apps, libraries, utilities that need compiled code, and doing it within the modern PyProject.tom and lock file paradigm. That still feels like an area ripe for innovation. We might see solutions that try to blend the speed and user experience of something like of with a more robust, maybe cross-platform mechanism for distributing and installing precompiled binaries. Perhaps leveraging technologies like WebAssembly or maybe standardized binary formats. The goal would be to make installing something complex, like a package with C extensions, feel just as trivial and reliable across all platforms as doing pip install requests is today for pure Python packages. It's about achieving the power of Conda's binary handling, but maybe with the workflow simplicity and standards alignment of tools like Poetry or PDM or Hatch. That could really unlock the next level of ease of use for a huge range of Python projects.
That's a really interesting prediction. A unified, fast, cross-platform binary solution built into the core tooling. Yeah, I can definitely see how that would be a game changer. Well, that wraps up our deep dive into the fascinating and sometimes complex world of Python's package management landscape. We really hope this conversation has helped clarify some of the confusion, maybe demystified a few things, and giving you a much clearer path forward for your own projects. We genuinely love to hear about your own experiences or insights. What are your favorite tools? Or maybe your least favorite? Let us know.
Yeah, absolutely. And just remember, knowledge really is your most powerful tool when you're navigating any complex technical landscape like this. The more you understand the why behind the tools, why they exist, what problems they solve, the better equipped you'll inevitably be to choose the right ones and ultimately build amazing things with Python.